Hello and welcome to the seminar number 6, more on decay modes. What are we going to talk about today? A short summary of seminar number 2, alpha-beta electron capture and isomeric transition, and then we are going to talk about some other effects regarding decays, such as conversion electrons, Auger electrons, Bremsstrahlung or braking radiation, and some other types of decay, such as the cluster emissions, spontaneous fission, other particle emissions, and better delayed emissions. So, a short summary of the alpha-beta electron capture and IT. The alpha emission is where a very heavy nucleus emits a helium nucleus, what we call an alpha particle. When this happens, the mass changes by 4 and the element also changes because the proton number decreases by 2. This alpha decay mostly occurs when a nucleus has a proton number of above 82, but with everything in chemistry and nuclear chemistry, for every rule, there are a lot of exceptions. So there are very many lanthanide isotopes that do alpha decay, even though they do not have a proton number of above 82. It's just a vague rule of thumb. Okay, the beta-minus decay is where a neutron changes into a proton and a electron is emitted from the nucleus. In this case, the mass doesn't change, but the proton number increases, therefore changing the elements. We have this very lovely example, the cobalt-60 from the cobalt-60 drop and run rods, and this happens mostly with a very neutron-rich nuclei. They are listed in the chart of nuclides below the valley of beta stability and are mostly marked in blue. We have the counterpart, the beta plus decay. This is where a proton changes into a neutron and a positron or an anti-electron is emitted from the nucleus. We have the example where I also made a video about sodium-22, which decays into neon-22. This happens when a nucleus has a proton excess. They are listed above the valley of beta stability and mostly marked in some reddish colors. As a concurrence decay mode for the beta plus decay, we have the electron capture. The electron capture is where a nucleus captures a K electron, so the innermost electron, and a proton converts with this newly captured electron into a neutron and a electron neutrino is emitted from the nucleus. We have the example mercury 194, which decays into gold 194, and for the electron capture can always happen if you have a proton excess. Beta plus does not always decay. There are few examples, such as mercury, where only electron capture can occur. So when beta plus is possible, you will always have the electron capture, but it's not the other way around. So when this electron is captured, we then have a hole in the K shell. This can be filled from electrons on higher energy level, and this drop in energy from the L to the K shell results in the emission of X radiation, which is why this radiation is sometimes also called K radiation, because it forms when a hole in the K shell is filled. Okay, we also have the isomeric transition. We have technetium-99, for example. This is just a nucleus in an excited state which decays, well, doesn't decay, does isomeric transition into a lower state, mostly the ground state, via the emission of a gamma quantum. But there's also another way for this nucleus to get rid of excess energy. These are called conversion electrons, or sometimes this process is called internal conversion. After a decay, the nucleus is not in the ground state most of the time, especially for beta decays, and this excess in energy has to go somewhere. In this case, it's transmitted to one K electron, so it's basically the opposite of the electron capture, and this K electron flies out of the atom, and this is what we call conversion electrons. It's preferred with lower excitation energies of less than 200 kiloelectron volts. They are marked in the chart of nuclei. As an example, we have bromine 80. The bromine 80M can either do isomeric transition and release a 37 kiloelectron volt gamma quantum and transition into the ground state, but it can also get rid of this excess in energy via this emission of, well, the conversion electron. And the most famous example for the isomeric transition, technetium-99M, which can do this isomeric transition transition via the emission of a 141 kiloelectron-volt gamma quantum, but it can also get rid of this excess in energy via the emission of, this conversion electron. So it's a bit like the reverse electron capture because, well, an electron is not captured but flown out. And it's the concurrent pathway to the isomeric transition. Since we then have a hole in the Decay shell, we will then have characteristic X-rays emitted from this type of decay, alongside with this conversion electron, of course. When this hole is filled, the X radiation can be transmitted to an electron within the same atom and then be flown out. And these electrons that are emitted from the X radiation that occurs within the same atom is what we call Auger electrons. This is basically an internal photo effect. We also have another type of radiation, which is called Bremsstrahlung. I like it because we have a German word that is established in the international room, sometimes called braking radiation. And it occurs when electric charges are accelerated or decelerated, i.e. changing their direction of movement. In this case, electromagnetic radiation is emitted. For example, if we have an electron, which is negatively charged, so we have a charged particle, and it flies near a highly charged nucleus, for example, the lead atom from a lead shielding, it will get decelerated via this attractional force between the positive and the negative, and then emits Bremsstrahlung. In this case, we have very harsh Bremsstrahlung because this deceleration is very fast. But it can also happen during the decay itself because, well, as you can see in the beta plus decay, we have a positive charge and a positive charge. At a certain point, these positive charges repel each other, accelerating this beta plus, and this results in the emission of electromagnetic radiation. This is not in the X-ray range, but in the very low energy range, but it's still considered Bremsstrahlung. The first case is also the reason why we do not shield high energy beta particles with lead shielding, but rather with plastic, because they are made up from elements that have a less concentrated positive charge in their nucleus. So carbon with a proton number of 6, it will result in the beta radiation to be decelerated bit by bit, therefore emitting soft Bremsstrahlung, which is not harmful for the human body. Talking about other decay modes, we also have the cluster emission. It's basically the alpha decay, but on steroids. It's a very rare type of decay, and for example, thorium-230 can emit a neon-24 nucleus decaying into mercury-206, which has a magic neutron number of 126. And there are also other types of cluster emission. For example, radium-226 can emit these carbon-14 atom in order to decay into lead-212. We in our lab will never be able to observe this type of cluster emission, in my opinion, because it is so rare. And as a definition, I've heard it's carbon-14 and above. And I'm not quite sure if this is the case because we didn't observe any cluster emission that has a mass of above the mass of an alpha, but below of carbon-14, or where the carbon-14 is just the next lightest element that could be emitted from the nucleus. We can see in the chart of nuclides this gray corner, which indicates the cluster emission, and additional to that, we have the nucleus that it's emitting. When we are talking about very heavy elements, we get to a point where they are so heavy that spontaneous fission can occur. Spontaneous fission is quite rare for uranium-238. One spontaneous fission for every million alpha decays, according to the Karl-Heinrich Lieser, and spontaneous fission is a concurrence decay to the alpha decay, which leads to lower alpha energies than some might expect, because you would expect, okay, we have a bigger atom that decays faster, and according to the Geiger-Nutter rule, we would expect a very high alpha energy. But when we are talking about very heavy elements, spontaneous fission becomes more and more pronounced. Therefore, it is a concurrence pathway to the alpha decay. The heavier, the more likely an atom is to do spontaneous fission. For example, we have Californium-254, which does spontaneous fission 99% of all decays. And Fermium-256 does spontaneous fission 92% of the time. There are also some other particle emissions that can occur when we are talking about the very edge of the chart of nuclides, so in the very proton-rich, we have cesium-112, which is a proton emitter. So a proton is emitted directly from the nucleus, changing the elements to xenon-111. On the other hand, we have in very neutron-rich nuclei, such as beryllium-13, the neutron emission, where beryllium-13 decays into beryllium-12. Well, the element doesn't change because a neutron is emitted and no proton number is being changed. Sometimes, after a beta decay, the daughter is in a such highly excited state that another particle emission is favored above the emission of very high energy gamma quanta. For example, we have the lithium-11, and these particle emissions that occur directly after a beta decay are called beta-delayed particles. We have beta-delayed neutron emission, beta-delayed 2 neutron emission, beta-delayed 3 neutron emission, beta-delayed alphas, tritons, and deuterons. In this case, the lithium-11 does beta-minus decay into beryllium-11, and this can either do normal beta-minus decay, but it can also emit a beta-delayed neutron, turning into beryllium-10, and so on and so on. For the beta-delayed 3 neutrons, we have beryllium-8, which is the smallest or lightest alpha emitter that there is. And for the beta-delayed alpha, we have helium-7, which is a neutron emitter. We also have some other types, and only 2 of these beta-delayed particle emission result in actually stable elements to be formed. With that being said, thank you for your attention and goodbye.